Okay, in this video we want to consider a surfaces of revolution problem, and we have defined the area of the figure that we're going to create. The equation is y squared equals 3 times x, and we're going to consider a part of the curve going from x equals 0 to x equals 2, and that part of the curve we're going to rotate about the x-axis to make a solid two-dimensional figure. So let's just kind of sketch it out. We notice here that x equals y squared. So y could have negative values, but x is always going to be positive because we're squaring y. And let's see, at x equals 0, then y will be 0. At x equal to 1, y is going to be the square root of 3. And x equal to 2, y will be equal to the square root of 6. So the curve is going to look something like this. 1, 2, 3, 1, 2, 3. We have 0, 0, of course, and x is 1. Y is the square root of 3, so it's a little bit more than 1.5. And then when x equals 2, y is the square root of 6. So that's going to be not quite 2. So the curve is going to look something like this. Like that, and this is x equal 2, and it's going to be rotated about the x-axis. And for that two-dimensional figure that we make by rotating it, we want to know what would be the area of it, its surface area. And when we're rotating about the x-axis, the area is equal to 2 pi, the integral going from x1 to x2 of y times the square root of 1 plus dy dx squared. Okay, now one thing we have to keep in mind though, we look at this integral over, we're integrating with respect to dx. So when we have the y value inside the integral, we have to express y as a function of x, and that's no problem. Y, the y here is just going to be the square root of 3x. And we need to find out what dy dx is. So we have this, y squared equals 3x, 2 times y times dy dx, that equals 3. So dy dx, that equals 3 divided by 2 times y. And that's correct, but something else we have to consider now. We're going to be squaring this, of course, and adding 1 to it. We're also going to be integrating with respect to x, so we don't want y in here. We want this expressed in terms of x variables. But y, we know, has this value. So you can say dy dx is equal to 3 divided by 2 times the square root of 3x. Or 3 divided by the square root of 3, we have the square root of 3 on top, divided by 2 times the square root of x. So we can write it like this, square root of 3 divided by 2 times the square root of x. So there's our dy dx, and let's see, we want to, for the integral, we want to square this and add 1 to it. So let's square it first. dy dx squared, that will equal, this will be 3 divided by 4 times x. And we have 1 plus that under a square root sign. So we have 1 plus 3 divided by 4 times x. That will equal 4x plus 3 divided by 4x. And we have this inside a square root sign. So we could write it like this, the square root of this divided by the square root of this, and that would be equal to the square root of 4x plus 3 divided by the square root of 4 is 2 times the square root of x. So this equals 1 plus dy dx squared. So let's go back to our integral now. It looks like we should be all set for it. The area equals 2 pi times the integral x1 to x2, x goes from 0 to 2, of y, that's the square root of 3x. I'm going to write it like this. The square root of 3 times the square root of x times the square root of this, and that's that right there, the square root of 4x plus 3 divided by 2 times the square root of x dx. So that would be our area integral, and it looks like these will cancel. These will go away. So this is equal to, put this on the outside, square root of 3 pi, the integral of the square root of 4x plus 3 dx. X goes from 0 to 2. And let's see, for the inside of the square root sign, if we call this quantity u, du should equal 4 times dx, which we have sitting right here. So that should work out all right for us. Let u equal 4x plus 3. Du will equal 4 dx. So now we can rewrite the integral. 4x plus 3, that's used for the square root of u. Du, that's 4 times dx, but we don't have 4 times dx. Here we only have 1 dx. So we divide both sides of this by 4. Now we're ready. So this will be equal to square root of 3 times pi, the integral, this is u inside here, so it's u to the 1/2, dx, that's 1/4 times du, so there's du, take the 1/4 to the outside, and I'm going to write it like this, x goes from 0 to x equals 2, because that's ultimately what we have to deal with anyway. So this will be equal to square root of 3 over 4 pi, and that's going to be, we add 1, so we're going to have u to the 3/2 divided by 3/2. That's times 2/3. Okay, and this will equal, this will give us 2 down here, this will give us a square root of 3 down here, so you have pi over 2 times the square root of 3 times u. But u is this, so we have times 4x plus 3, quantity raised to the 3/2 power, and x goes from 0 to 2. So this right here is going to be the area. So let's see. Let's just make some room here. So it looks like the area will equal pi over 2 square root of 3 times x equals 2. 4 times 2 is 8 plus 3 is 11. So you have 11 to the 3 halves minus x is 0. That's 3 to the 3 halves. And that would be our area. Okay, so hopefully that was worthwhile for you. And again, this is considering surfaces of revolution when we are rotating about the x-axis to get the area integral. Also, there's a way that we can set this up in case we have a parametric type situation where maybe x is equal to some function f of t and y is equal to a different function, say g of t. We could modify this equation accordingly to give us a surface area. We'll try and solve a problem like that in the next video because those problems turn out to be a little bit more complicated than the example here that we dealt with. So come back and join us for that video. We'll try and solve perhaps a little bit more of a complicated problem.